In this episode, one of the world's most cutting-edge factories.
Behind me is one of the largest hydraulic stamping presses in North America. It's actually 7 stories high.
A high-tech mission to build an alternate future.
It's an absolutely brilliant piece of engineering, and suddenly, science fiction isn't tomorrow, it is today.
And the pioneering historic innovations.
At its height, they could assemble a galley per day here, which is truly incredible.
This beautiful machine, it's one of the world's first electric cars. Brilliant engineering.
That made the impossible possible. Since the birth of the Industrial Revolution, factories have rarely been seen in a positive light. Often portrayed as dirty, grim, dangerous places, churning out products at the expense of their workforce. But the 21st century factory can be a very different place. This is the Tesla factory in Fremont, California. An extraordinary, state-of-the-art automotive manufacturing facility that's at the vanguard of a new era of motoring. Alexis Georgeson has witnessed this giant industrial machine come to life.
The processes here in this factory are designed to be efficient as possible. It's a 5.3 million square foot facility. In meters, that's 500,000 square meters.
In 2008, the American car manufacturer broke new ground when it launched the world's first electric sports car. But while its car designs might be revolutionary, the company's mission to change the motoring landscape and bring electric cars to the masses presents a different kind of engineering test, one on a much greater scale.
That's one of the biggest challenges ahead, as our CEO Elon Musk has said, is really building the machine that makes the machine.
And that machine fired up for the first time in 2012. Under one roof, human workers combine with hundreds of robot colleagues to turn raw materials into high-tech vehicles in a matter of just a few days. Man and some of the world's mightiest machines come together to cast, stamp, paint, and assemble component parts into 2,000 cars every week, before they are put through their paces on the factory's dedicated test track. It's an engineering achievement that would have once been thought impossible.
We're rethinking the way that the automotive industry has approached production in the past through first principles of physics and through vertical integration, and just really treating this as an engineering problem first and foremost.
Once upon a time, there was no such thing as mass production.
Sword, please.
Everything was artisan-made.
Thanks, peasant.
Charming and unique, maybe. But inconsistent.
What a chopper!
Mine's a tiddler.
Expensive.
More. More. More.
And slow. It was far from the ideal way to produce things en masse.
What's this? Gah!
But a change was on the horizon. Architect and historian Benedetto Camerana has come to the historic Italian city of Venice. Now famous as a picturesque tourist attraction, it was once one of the most dominant states in the world.
In the Middle Ages, the Republic of Venice was a political power with a strong reputation for war and conquest.
The success of the Venetian Empire was based on a rich combination of trade and naval muscle. Both needed ships, and lots of them.
Naval boat building had been carried out in different shipyards, sprawled throughout the city. But as demand grew, the shipbuilders were faced with a problem. Using the traditional method, it would take weeks to produce a single galley, and that was not fast enough.
In the 12th century, the Venetians came up with a game-changing solution.
And this is it, the Venice Arsenale. Here they completely reimagined the way that ships were built.
For the first time, each individual component of a ship was mass-produced in one place, with all the specialist workshops laid out around the sides of a basin.
Instead of staying in one spot as they were constructed, the ships were moved around the dockyard to different workshops, each focused on prefabricating the different elements of the ship.
Hulls were made and launched as shells. They were then towed across the shipyard to be fitted in sequence with ready-made masts, rudders and anchors. Finally, they were rigged and kitted with oars and armaments. The process reduced build time dramatically.
At its height, they could assemble a galley per day here, which is truly incredible.
The Venetian shipbuilders had invented the production line. And several hundred years later, the ideas pioneered at the Arsenale were adapted for a completely different form of transport. In 1916, engineer Giacomo Mattetrucco was asked to design a bespoke factory in Turin for car company Fiat. What he came up with was truly remarkable. The Lingotto.
When it was completed in 1923, this was the largest car factory in the world. 500 meters long, 5 stories high, Mattetrucco's brainchild eclipsed all its predecessors in terms of size and innovation.
For the first time, all elements of a building were designed to work in harmony. Specialist workshops were placed strategically on each floor, producing parts that would be fitted to the vehicles as they progressed through the factory.
Raw materials would arrive by rail to the ground floor of the building. Here, they would be fashioned into car components. On the second floor, the engines and bodies of the car were made. 1 story up, gearboxes and steering were added. The 4th floor specialized in brakes and upholstery. And on the 5th floor, finishing touches were made. Finally, the completed cars would emerge on the roof, the most iconic feature of the building.
All the cars coming off the Lingotto production line were brought here, a purpose-built rooftop test track.
For nearly 60 years, this phenomenal test track, high above the Turin skyline, would have been witness to the birth of hundreds of thousands of cars. It's amazing to think that the car I'm driving now was taken for its first spin up here on the 21st of October, 1936.
The Lingotto factory produced its last car in 1979, having operated successfully for over 50 years. But its legacy lives on. At the Tesla factory in Fremont, California, the principles first applied at the Venice Arsenale and further developed at the Lingotto are being given a 21st century makeover.
The way we move cars from one end to another, the materials that we're using, the fact that so much of the factory is vertically integrated, which means that we're actually producing so many components here in-house rather than shipping them from other parts of the world or other parts of the country.
While the production line principles remain the same, the setting is almost unrecognizable from factories of the past.
We wanted this first and foremost to be a beautiful working environment that really was a testament to the quality of the products that we were building here. So we came in, we repainted the entire space, we put sunlights in the roof, we wanted a lot of natural light and a place where workers could come and be proud of the craftsmanship and the space where they were creating these products.
But to create a truly modern factory, the manufacturers need technology to match. And for that, today's designers can draw on the great innovators of the past.
The robot is correcting itself to achieve its objective. And that's what makes these robots so amazing.
To deliver their impossible engineering. Engineers at the Tesla electric car company are in the process of creating one of the most advanced production lines on the planet. Its mission? To produce electric vehicles in quantities never before witnessed. The 500,000 square meter factory takes raw materials in at one end and, in as little as 3 days, transforms them into cars. 6,000 workers interact with the most modern of technologies to produce 2,000 electric cars a week. All of which are then put through their paces on the dedicated test track. To produce vehicles on this and an ever-growing scale means overcoming a major challenge.
How do we streamline this? How do we ramp production? How do we keep the costs down? And how do we make this manufacturing process as efficient as possible?
The solution lies with one of modern history's most significant breakthroughs.
It's a beautiful knot you're doing right there.
Science communicator Kate Mulcahy has come to southwest England to find out how a study into brain function led to a breakthrough in robotics.
Oh, Lord Lloyd. As I attempt to cross this beam, signals are being sent to my brain through my eyes, my inner ears, and my sensory systems. This feedback helps me to correct my weight distribution, and hopefully I won't fall.
Each time Kate feels herself deviating from her route or losing her balance, her senses warn her. This has been called negative feedback, an ability that helps all living creatures to adapt to the environment around them.
Yes!
It's a sophisticated process that engineers and scientists attempted to build into early self-governing machines. And by the mid-20th century, a new approach called cybernetics seemed to have cracked it. At the vanguard of this new science was American-born neuroscientist William Gray Walter. In 1948, in Bristol, England, he built a revolutionary machine to test his ideas.
And here it is. This is the replica of the machine developed by Walter in 1948. Each machine contains 2 valves, 2 relays, 2 motors, and 2 sensors, one for light and one for movement. So essentially, it's a two-cell nervous system, which when you think about it, compared to the billions of nerve cells that are in our brain, isn't that many, but it still did something really amazing.
Grey Walter called his device the tortoise, not just because of its looks, but also because of the lessons it taught us.
The tortoises are designed to sense the light and move towards it. So, you can see it heading towards the light bulb right now.
The tortoise is using a photoelectric cell to detect the light.
That's the sensor you can see on top of it moving back and forth. When it registers the light, it stops the steering and moves towards it.
Because there are different light sources in the room, the tortoise is regularly stopping to check its position before adjusting its direction to get closer to the brightest light.
So that's negative feedback. Just like when I was balancing on the beam and adjusting myself, the robot is correcting itself to achieve its objective. Now, if we put obstacles in its way, things get really interesting.
The shell of the robot is now also acting as a bump sensor.
So it's making decisions based on two sensors. One is sensing the light, and the other is detecting the obstacles.
The result is an example of complex behavior. The tortoise has a different solution every time the experiment is run, and each route involves a multitude of different corrections and movements.
And that's what makes these robots so amazing. Every reaction they make is a result of sensing the environment around them. Then they react and create a new path. Amazing.
For the first time, a machine could demonstrate a complex decision-making process, and the discovery paved the way for a revolution in robotics. Bristol remains a world-renowned centre for robotic innovation. And at the Bristol Robotic Laboratory, they're exploring everything from surgical robots to robots that can fly.
Autonomous machines have come to replace humans in many realms, from the domestic to outer space, and they've revolutionised the industrial world.
At the Tesla factory in California, they're integrating robots and workers to a much greater degree than the factories of the past, making it one of the most automated facilities on Earth. Some even have echoes of Grey Walter's revolutionary tortoises.
Solved a tough logistics problem in the factory too with the use of robots. So our cars actually move around several sections of the process of production on these little smart carts. They're robots that actually follow these magnetic strips in the floor, and they move from one section to the next following these little strips.
Like the tortoises, these automated guided vehicles can spot people or objects in their way and will wait until the path is clear. They'll take themselves out of rotation when their batteries run low and put themselves back when fully recharged. And the simple guidance system means their routes can be adapted in an instant.
We can easily pick up these magnetic strips. We have the flexibility to change the lines and to change the direction that the cars are going very seamlessly.
But the carts are relatively primitive compared with most of the factory's robots.
The robots behind me are KUKA robots. They're actually trained to do up to 5 tasks. They rivet, they weld, they glue, they move pieces from one part of the line to the other. So they're incredibly smart robots.
Hundreds of these robots perform amazingly complex but repetitive tasks, with unerring accuracy and without ever getting bored. But when it comes to the job of lifting and carrying entire cars, engineers at Fremont had to look to some serious heavyweights. Kate Mulcahy has travelled to Coventry in England to find out more.
This is one seriously impressive robot. I can't believe how massive it is. This is the Fanuc M2000 IA1200 multi-arm manipulator. Now we're really lucky today. We get to come up close and personal. Normally, there's caging all the way around it for safety. Now this robot is so strong, it's capable of doing 4 times the work of a conventional robot. It's able to lift a really impressive 1.2 tons, and it's used on the Tesla assembly line. But its bigger brother, which is also in use on the Tesla assembly line, can lift a huge 2.3 tons. Now that's really useful if you want to move a car in a single lift. So most conventional robotic arms that you'd find in the market wouldn't be able to lift weights nearly as close to this one. On top of that, this robot is capable of running 24 hours a day and 7 days a week. Now, I've had a quick lesson on how to operate it, and hopefully, if I've done it right, yes, it's working. Traditional ways of moving heavy weights, such as lifts or hoists, can only go up and down, whereas this, because of its 6 different axes, allow this robot to move with unbelievable accuracy. It's exactly this that Tesla uses to save them both time and money, and to ensure that cars can keep rolling off their production line. And all of that makes this a truly incredible feat of robotic engineering.
And in California, 12 of these heavyweights provide the mechanical muscle to keep the factory production line going. Named after Marvel characters, the likes of Wolverine and Iceman lift up to 2,000 cars a week without breaking a sweat.
Robots are incredibly valuable in the automation of this process and helping us to ramp production and to make this process as seamless as possible.
But robots aren't the only remarkable machines required for a 21st century car factory. Its engineers will need to look to history's most innovative pioneers.
There was an amazing jump in engineering, and his methods were picked up by Henry Ford and other pioneers of the automotive industry.
Oh, that's great. So it's actually pulling the paint all around onto the back.
To create yet more impossible engineering. In Fremont, California, one of the world's most cutting-edge factories is being created to satisfy a 21st century challenge.
All of this is an effort to build as many electric vehicles and get them on the roads as quick and seamless as possible.
The state-of-the-art Tesla factory is capable of building electric cars in the kind of quantities once reserved for petrol vehicles. Currently, over 2,000 each week, and it's still growing. But producing electric cars quickly, efficiently, and economically means overcoming engineering obstacles once thought impossible.
The way that other manufacturers have built electric vehicles in the past was to basically gut internal combustion engine vehicles and put battery packs wherever they would fit. But we built the car from the ground up.
And what will eventually become a car arrives on the site in the most basic of formats.
Behind me are giant coils of aluminum. This is the start of production for these vehicles. It's the raw material that comes through this end of the factory. There are 20,000 pounds of aluminum coils.
Traditionally, most motor cars have been produced from steel. But electric vehicles face a unique challenge. The batteries that drive the electric motors are heavy. That's why the manufacturers have chosen an alternative raw material. One that's more familiar in the aerospace industry.
Aluminum is incredibly lightweight, very durable, and safe. We've really designed these cars from the ground up to maximize safety and efficiency, and aluminum helps us do that.
But how can you turn sheet aluminium into car body parts quickly and accurately enough to make production cost-effective? It would be an impossible problem without one of history's most successful innovators. Today, bicycles are commonplace. But when they first appeared, they were strictly the playthings of the rich. Historian Chris Sweet is on the trail of the innovation that transformed the cycling world.
Late 19th century bikes were luxury items, costing up to $100 each. That was as much as an average worker would make in 6 months. But all that changed here in Chicago.
And the man behind the bike revolution was entrepreneur Adolf Schöninger. After losing his toy business in the Great Fire of Chicago in 1871, Schöninger was determined to recover. And the growing popularity of bikes looked like a promising avenue to pursue. However, early metal bicycles were all manufactured using the same basic process, a technique Schöninger was keen to improve.
Traditional method of making bicycle components was known as drop forging. It involved taking a chunk of metal and heating it till it was malleable, like this chunk of clay, and forging it into shape by repeated pounding. It was a long, labor-intensive, and expensive process. That is what Schöninger wanted to change. And this is what he did. He came up with an industrial press to shape cold steel. Imagine the sandwich maker is our press. We put in this sheet of cold steel, press it, out comes a three-dimensional bicycle component, ready to be assembled and painted.
By pressing components instead of forging them, Schöninger's Western Wheel Works was able to slash the price of its bicycles, making them accessible to the general public.
This is an original 1898 Crescent number 18, made by Western Wheel Works. If we look closely, you can see the parts on this bike that would have been stamped. The seat tube junction here would have been a stamped part, as well as the crank hanger down here, the head tube, even the handlebars and the pedals would have been stamped. Initially, Schöninger was only stamping a few parts of the bicycle, but it only took 5 years before he was stamping every part that he could.
Soon, Schöninger's business was turning out 70,000 bikes a year, with markets as far away as Europe. And as other manufacturers followed suit, Chicago became the bike capital of the world.
It was an amazing jump in engineering. Schöninger's innovations soon led the way to cheaper bikes, and his methods were picked up and used by Henry Ford and other pioneers of the automotive industry. He really was an amazing engineer, and the mass stamping of parts revolutionized manufacturing in America and around the world.
In California, they're taking the techniques pioneered by Adolf Schöninger and supersizing them.
This is one of the largest hydraulic stamping presses in North America. It's actually 7 stories high. We can only see 4 stories. 3 of them are actually underground. There are 5 main sections of this press, each one weighing up to about 1 million pounds.
The giant stamping press uses a variety of heads to turn the flat sheets of aluminium into all manner of ultra-lightweight car body parts. And by cold forming the aluminium, it helps preserve the strength of each component.
You need a machine that that can exert a ton of pressure and force down on those panels without a lot of heat. That's what this hydraulic press is capable of doing. We take those sheets of aluminum that you saw, and they're actually stamped between 4 to 5 times as they move down here.
The press is capable of exerting 8,000 tons of pressure per square inch, the equivalent of having 3,000 cars on your thumbnail.
Each one of these sections exert 4,500 pounds of force as they come down on those pieces.
The 7-story tall monster press can create strong, complex shapes quickly and at a much lower cost than hot forming or machining from solid.
This is an incredibly important machine to us to help stamp the individual parts for Model S and Model X. They're electric vehicles, and they're already very heavy cars because battery packs weigh a lot. So it was important that the other parts of the vehicle be as lightweight as possible for efficiency. The aluminum panels make the range and the safety very, very possible in these cars.
These fresh-pressed panels also need to be painted. And while the army of robots can help, this ultra-modern process would be simply impossible without a blast from the past. Physicist Susie Shee is visiting an inner-city graffiti workshop to discover how one man and a salt shaker revolutionized the world of industrial painting.
Spray painting is a brilliant way to cover a surface area with an even coat of paint. But as any graffiti artist can tell you, it's pretty messy and inexact. As the paint particles are released from the pressurized canister, they have a tendency to go everywhere, all over your hands and the floor. And that leads to a lot of wasted and scattered paint, which is both costly and inefficient.
In the Depression of the 1930s, Harold Ransberg was facing the same problem. He'd been forced to abandon his university studies to help at his father's homeware factory. There, he spotted the waste during spray painting.
This salt shaker is exactly the kind of article that Ransberg was trying to paint. So if I try and paint it, you can see there's a lot of mess and a lot of wastage, and I haven't even really achieved a very good finish. You can imagine on an industrial scale how expensive that would be.
Along with lab assistant Harry Green, Ransberg began looking for a solution.
We all did this experiment in school. If I take a glass rod and rub it with a woolen cloth and then hold it near a balloon, the balloon is actually attracted to it. So what's happening is when I rub the glass rod, friction means that electrons go from the cloth to the rod. So then the rod is negatively charged.
Negative and positive charges attract each other, and Ransberg and Green thought this could provide the key to a new form of spray painting. In the spring of 1938, Ransberg spent all the money he had, $35, to buy a high-voltage transformer usually used for hospital X-ray machines.
I'm going to use a Van de Graaff generator instead, but the principle is more or less the same.
The generator uses a moving belt to build up charge in a hollow metal globe. Like Ransberg's transformer, it produces high voltages but at a low current.
So if I connect this up, that will give a positive charge to the shaker, and then the paint, which is still neutral, is going to become attracted to it, just like the balloon was attracted to the charged rod. At least that's the theory. All right, so if I just ground the paint tin, switch it on. Let's see. Oh, that's great. So it's actually coating all around the sides. It's actually pulling the paint all around onto the back. It's got a really good coverage, and actually I think there's a lot less paint wasted as well.
Ransburg's invention was a great success, and after further refinements, his patented painting process took off globally.
You might not realise it, but electrostatic painting is used to decorate all kinds of everyday objects, from shop fronts to railings, lampposts to bicycles. We are surrounded by the fruits of Harold Ransburg's innovative approach to painting.
"80 years on, the factory in California takes electrostatic painting to a level that Harold Ransburg could only have dreamed of. In a state-of-the-art paint shop, each car is attached to an electricity source and grounded. Positively charged paint is then sprayed, electrostatically attracted to the car. Primer, colour, and finally a clear coat are applied to create a completely flawless finish. But mass-producing electric cars effectively and efficiently isn't the only challenge the factory faces. It must also produce a product that the petrol-headed public actually want to adopt. Turning history into high-tech.
20 miles an hour. I'd say that's about as fast as I'd like to go.
To create even more impossible engineering. In California, a group of engineering innovators are busy creating a factory of the future. Attempting to turn a more than century-old industry on its head. They're using advanced technology to turn the electric car from niche item to everyday mass-market product. Everything about the 500,000 square meter facility is designed for speed, accuracy, and efficiency. But those aren't the only challenges the factory faces. It must also turn out a product that a public, brought up on the internal combustion engine, will actually want. It was 1908 when Henry Ford had a bright idea. Bringing the internal combustion engine to the masses. The newfangled technology changed the world. Demand for gasoline went through the roof.
I'm rich.
Cities swelled, new sprawling suburbs within reach of the workplace.
Hi, honey, I'm home.
Life became centered around the internal combustion engine. And people could go faster and further than ever before. But surprisingly, once upon a time, man's love affair with the combustion engine had a rival.
This is a Pope Waverley. Built in 1901, it's one of the world's first electric cars. And this particular one was used by Harrods for deliveries.
Physicist Susie Shee is taking a ride on an original piece of vintage engineering that once competed for the title of King of the Road.
It's a little known fact that at the turn of the century, about a third of all cars were electric powered.
At the birth of the car, there were three main methods of propulsion: internal combustion, steam-driven, and right up there on the list of most popular, battery-powered.
Now this beautiful machine, in its day, would have had a range of about 20 miles and a top speed of a whopping 20 miles an hour. But having driven in it for a while, I'd say that's about as fast as I'd like to go.
But while this US-developed Pope Waverley might have been the perfect solution for delivering luxuries to London's well-heeled, electric cars were soon eclipsed. As petrol cars developed a longer range, got more reliable and faster, the feeble electric car was left standing. The designers and engineers at Tesla feel they've found the key to overcoming what's held back the electric car for so long. Motoring journalist Alex Roy is taking the Model S out for a test drive.
Earlier generations of electric vehicles didn't have the benefit of batteries with decent power density. It is the first time that you have an electric vehicle that's a genuine sports car. The Model S, you can do this. And that is Ferrari level acceleration. It's impressive.
At the heart of the design is the powerful electric motor. And it couldn't be more different from a traditional internal combustion engine. Compared to a standard gasoline engine, which has hundreds of moving parts, the Model S and Model X motor has only one moving piece: the rotor. Powering it are nearly 7,000 small lithium-ion batteries, packed into a tray that fits in the floor of the vehicle. And to produce them, Tesla is doing something extraordinary. Creating another factory, the size of which has never been seen before on planet Earth.
It's still under construction. We're building it in phases so that we can actually start production of batteries, cells, and packs inside while we continue construction outside. That factory will, once complete, be the largest building in the world by footprint.
The so-called Gigafactory in Nevada will hold the key to the mass production of electric cars on an unprecedented scale.
Within a couple of years, we'll be putting hundreds of thousands of battery packs out every year.
The batteries, combined with radical design, mean electric cars can now match their petrol counterparts for range.
Regenerative braking is a technology that grew out of racing. And in Formula One, regenerative braking was developed to make cars go faster. In a Tesla, that extends the car's range. And it's one of the reasons the Tesla has a range of 300 miles as opposed to earlier generations of electric cars, which are restricted to 250, 200, even 150.
Anyone who's ever ridden a bicycle will realize the amount of power that's wasted when you brake. All that kinetic energy from your forward motion is thrown away as it converts to heat in your friction brakes. Just how much is painfully obvious when you have to pedal yourself back up to speed. But with an electric car, the motor can be used alongside the brakes to slow the vehicle and at the same time act like a generator, converting kinetic energy back into electricity that can be returned to the batteries.
If you didn't have a regenerative braking system dumping power back into the battery, I would imagine you'd have somewhere between a 10 and 30% drop in range. It's an absolutely brilliant piece of engineering. And suddenly, science fiction isn't tomorrow, it is today.
These trailblazing examples of engineering would not be possible without the giant machine that builds them. An extraordinary engineering process in its own right that begins with coils of aluminium sheet and ends just a few days later on the test track.
That can-do, think outside the box is really something that informs both the vehicle and the factory side of the equation here at Tesla. You'll see that both in the engineering of our products as well as the engineering and in our approach to manufacturing and production within this facility.
By drawing from the innovators of the past,
This was the largest car factory in the world.
Oh, that's great.
Amazing.
adapting their ideas, and making trailblazing discoveries of their own.
Every single manufacturer will be making a car just like this with their own brand on it within 5 years. Things can be done better. You don't have to be trapped in the past.
The planners, designers, and engineers behind this futuristic factory are succeeding in making the impossible possible.
Being in this factory certainly is something that I think every employee can agree is something they're incredibly proud of.